Okay, let's start. So welcome to the last colloquium of this semester. And it's my great pleasure to introduce Professor Kyu-Hwan Lee from University of Connecticut. He is also visiting scholar this summer, as a guest scholar. And he will give today he will talk about advancing combinatorics and number theory with AI. So let's welcome you.
I thank Valentin and Kyung-Suk for inviting me, giving me this opportunity to speak. This is a joint work with Kyu-Hwan, and then Blake Jackson and Xiu Lee. Xiu Lee went to postdoc, so he was an undergraduate student here. Now he graduated from UC Berkeley this May. Okay, so these days, mathematicians and other people are talking about AI mathematician. So the question is, can we build an AI mathematician that conducts mathematics research autonomously? So we don't need to teach, at first we have to build, okay, after the training, the AI mathematician will conduct mathematics research by itself. Can you do that? And some time ago, 20 years ago, this sounds like a dream, but not anymore. Because last year, for example, DeepMind made a model, in particular some version of Gemini, and then the model achieved the IMO gold medal. So there was a big surprise last year, but it's only 1 year ago, less than a year ago. As you can see, this news came out July 21st. So it's less than a year ago this happened. And then this is not a surprise anymore. So we understand the level of AI is far surpassing the level of IMO gold medal. And some leading mathematicians in the world got together and then they proposed 10 research problems. Then they knew the solution, but they didn't publish the solution to anywhere. So the proofs were basically somewhere in their disk where the drawers of the desk. And then nobody knew the proof. And then they suggested those 10 problems as a challenge for the AI system. Can AI system solve those problems, research problems, autonomously? And that happened this year, March 17th. So probably you may recognize some mathematicians here. These are all leading mathematicians. Mohamed Absaid, and then the last one is Lauren Williams at Harvard. And then they proposed 10 questions. And then by now, I didn't really closely follow the developments. I believe about half of them are already solved, even though this was a research level problem, and then the literature didn't have any proof. But AI autonomously already found out the proofs of at least half of the problems. And then soon there will be a report about that. So then, again, the AI is it's now at a research level. Very recently, probably many of you saw this news. It's only May 20th, so how many days? 2 weeks ago. The OpenAI model, I think it's ChatGPT Pro, disproved a central conjecture. So it's one of the Edoshi conjectures in discrete geometry. Then again, it autonomously found out could disprove the conjecture. And then many mathematicians were very surprised by this because it is a problem in discrete geometry. The details can be found easily, so you can just Google and then read the article. The discrete geometry, but the solution came from something in number theory. So the AI model brought in the ideas from number theory, class field theory, and then they made a connection and then disproved this conjecture. There was a big surprise because it's like two mathematicians, one in discrete geometry and the other mathematician in number theory. They talk to each other and then it's like giving a solution. But it's done by AI itself because AI knows number theory and also discrete geometry. So in some sense, this was easy. Not easy, but this was possible. ChatGPT. So as you can see, things are developing, and it's not a fiction anymore. In a few years, we don't know how long it will take, but in the future, we'll see AI doing research mathematics autonomously. But if this develops, then I believe all of us are mathematicians. We feel like we are outsiders. We are just watching the sports game and then we don't really play the game. But hopefully it will take time. So even though it develops so fast, it will take time. Meanwhile, these things are developing as mathematicians. We may try to do collaboration. I think that's maybe more fruitful direction. Then these developments are usually done by big tech company. We don't have that many GPUs. So for us, we are more interested in, personally in particular, we are, and actually I am very interested in human AI collaboration. So question is, can AI assist mathematical discovery? So that can be a good question. Then there may be many approaches and paradigms. So you can apply machine learning or AI tools to research problems. Sometimes we obtain new record-breaking examples. Then example tells everything. So examples tell you everything. So that's good. Or counter examples, and then like a conjecture will be disproven. Other times that is not sufficient, and in many cases we have to interpret the results, discover new patterns. So the AI itself doesn't give you any explanation. It does something, but we need to interpret the results, and then human mathematicians can discover some new patterns. Then, of course, it will lead to conjectures. And then we can prove or disprove the conjectures. Here we may use AI again. But anyway, in this way, we can play the game together with the help of AI. And this may be a very fruitful direction because now we have powerful tools and methods coming from AI.
By the way, what kind of AI are you talking about?
So any kind you can think of. And then here, I will show you two examples. Good question. So before we go to the examples, the interpretation is the key step in human AI collaboration. So we want to understand how the machine learning or AI system think. Okay, then that's interpretation. Then as a human beings, we can see new things. So in order to be more concrete, and in order to answer your question, so I will present two examples. The first example is Galois groups. We study Galois groups in undergraduate abstract algebra or in graduate school abstract algebra. And here we'll use decision trees. So it's a very classical machine learning algorithm. So we'll interpret decision trees, and surprisingly, we'll obtain new criteria to determine the Galois groups. So this can be very standard, but also in some sense ancient or traditional method. But still, we can find something new in this approach. So I will show you this example. The second example is a DICE in algebraic combinatorics. So here we'll interpret transformers. Transformers are the base models for large language models. If you know the story and the history, then Google DeepMind researchers made these transformer models, and then for like a translation task, then it turned out that it performs really well for like a language processing, and then it became the ChatGPT. That's only about 9 years ago, 2017. But now the transformers are widely used for, essentially used for large language models. We'll consider very simple transformer models. Then we'll interpret those models, and then we'll obtain a new algorithm for bijection. Okay, so I will present these two examples. I hope that I can finish these two examples in 1 hour. So first, the Galois groups. Let me remind you what a Galois group is. To consider a number field K, then it's a finite extension of Q. And a number field K is called Galois if the automorphism group of the field over Q is the same as the extension degree. And then in that case, we define the Galois group as the automorphism group of the field over Q. So how can we compute the Galois group? Of course, there are some algorithms. Then first, low degree polynomials, you do this computation in abstract algebra exercises. So here is an example. Now, can you compute the Galois group of this polynomial or this field? Then, it will take time. There is an algorithm, but it will take time. So how many possibilities are there? Then how many abstract groups are there in order 8? Of order 8? I mean, this is an order 8 Galois extension. Then we have 5 possibilities. And then which one is the Galois group in this case? Again, we have to calculate. And then even though there is an algorithm, it takes time and then it's not straightforward. But can we use machine learning for this problem? Can you teach a machine to determine the Galois group? It's obviously non-trivial. And then it's difficult for human beings. Then why don't we ask a machine learning model to do this job and then see what happens? Okay. That was the question we asked a few years ago. And then, so here is the experiment. The first question is, we have to answer this question, how can you present a number field K? Number field K is an abstract thing, but now you have to present it to a machine. So, and a machine sees only numbers. I mean, like a number, of course, but it's like if it is like a picture classification, then machine learning can classify pictures of dogs from pictures of cats. Okay, but what is a picture? A picture is a sequence.
What is your definition of machine learning?
Oh, that's a good question. Okay.
That is actually your tool, right? To interpret your
My definition of a machine learning.
yeah, what's your definition?
Oh, okay. Let's talk about it later. That's a very difficult question.
Yeah.
But here, I will talk about this decision tree. So it will become more concrete. It's okay. Picture. Picture is a sequence of numbers. So we will present number field K using a sequence of numbers. Picture is at the end of the day. It's you only know or machine only sees the pixels. Okay, then each pixel has some numbers, and then it's a matrix of numbers or sequence of numbers. So in this case, we use Dedekind-Zeta function. It's a generalization of the Riemann-Zeta function. So if you have a number field K, then you can consider ideas instead of the numbers. It's a generalization, but it is written as after you collecting the same denominator. It's some coefficients, and then denominator is MPDS, as in the Riemann-Zeta function. Okay, and these coefficients carry the essential information about the number field. So all represent or present this number field using this sequence. So from A1 to A1000, then it becomes like a picture of the number field K. Of course, we choose the Dedekind-Zeta function because it has been studied a long time, and then basically one idea in number theory is to use zeta functions and L functions to study arithmetic objects. So we are following the traditional. So the experiment will be like this. Now we have a family of number fields. And then we have a picture of the number field for each number field. So this sequence is like a picture. And then we want to classify those number fields according to their invariants. So it's not very different from classifying pictures of dogs from pictures of cats. Okay, so in 2022, Yang Hu-hyo and myself and Thomas Oliver used logistic regressions to study and random forest to predict Galois groups and other invariants of the number fields. And so we observed very high accuracy, about like 95% or higher. Somehow, machine learning could determine these invariants with a very high accuracy, even though the machine learning model didn't know anything about Galois theory. But somehow, this approach produced a very high accuracy, and we were very excited. And then we considered other objects like elliptic curves, genus 2 curves, and many other things. So we didn't have time for interpretation at the time. So there was no interpretation for why it worked so well. But we just observed this. Then Xiu Li approached me, and then we had a discussion. And he was very interested in interpreting the result. And then we decided to use the decision tree model because it is very easy to interpret. So what is a decision tree? So you have features. So in our case, from A1 to A1000, and then you find out a feature which divides the data set most efficiently. That's one division. And after that, you find out another feature which divides the set the next most efficiently, etc. So we will see a picture, and then we'll see what happens here. And then that's the basic idea of a decision tree. So once it works, and it's very easy to interpret. So I will show you an example soon. So the first experiment was we consider degree 9 Galois extensions. Then there are two possible Galois groups. So if you remember what you studied in abstract algebra, there are a cyclic group of order 9, or the product of two cyclic group of order 3. There are two cases. And then in a database of these number fields, LMFDB, that's the name of the database. At the time, there were 1,266 degree 9 Galois extensions. So we had a decent number of Galois extensions. And then we had this many C9 fields and then that many C2 squared fields. So we computed the dedicated Zeta coefficients and then did the machine learning experiments. So we asked the machine learning model to distinguish between C9 from C3 squared. Then what happened? The accuracy was 100%. It was perfect classification. Oh, it was surprising. Then decision tree is very interpretable. So we saw the decision tree, and this was the tree. So the model was looking at A1000, and then if it is less than 5, less than like 4, or equal to 4, then it immediately says that it is a C9. Then after that, it looks A343, and then 0.5 means basically it's 0, less than, because all of these are positive numbers. And then C9, otherwise it's C3 squared. And then this decision tree achieved 100%. And then what's the common feature of 1,343 and then 27? What are these numbers? These are 27, that's easy. 343, then 1,000. These are all cubes. Oh, okay, then somehow the machine learning model knew that we have to look at the cube of a cubic number. Okay, cubic coefficients of the dedicated Zeta function is important to determine these two Galois groups. Okay, it was a very interesting. Then, of course, we can make a conjecture. So the conjecture was, if A subscript P cubed is 0, then Galois group is C9. There was a prediction from the decision tree. Okay, and then of course we tried to prove it. After making this conjecture, we tried to prove it using algebraic number theory, and then it turned out that we could do more. So decision tree only showed us this prediction, but while we are trying to prove it, we could do more. Actually, it was an if and only if. And then if you were in this situation, then what's the next step? So you are mathematicians, then P cubed and degree 9. Obviously, we replaced the 9 with the L squared. L is another prime. And then P cubed is replaced by P to the L power. And there was a natural generalization. And indeed, we could prove this. And then we realized that this is a new theorem. The proof uses algebraic number theory. And then I cannot say it is like a super hard number theory problem. But it is new because nobody has ever considered this problem this way. So the traditional way is really different from this approach. And then from this data scientific and machine learning approach, we could see the problem in a totally new perspective, and then we could obtain this theorem. And then good news was this was possible. I mean, possible for us to prove this theorem.
So you design your machine learning, right? We have your own machine learning, right?
This is
Such a tool
uh,
predict like that, right? So you don't give me your machine learning. So I'm still curious about what kind of your machine learning you are using.
decision tree, this example. But decision tree is a very standard machine learning algorithm.
This kind of matrix props can predict you have some polynomial, right? But I don't know, but I'm actual numerical analysis.
Yeah.
So you want to factorize some polynomial. You want to predict some coefficient of some factor, right? Polynomial. So maybe you use some problem, some algorithm, I guess. I wonder what kind of your algorithm you use.
Yeah, well, I think we'll have to discuss it later.
Yeah.
But we have a polynomial that defines a number field.
Yeah.
Number field gives you a dedicated error
So
function.
why your tool calculates your result?
Here is the answer. So the decision tree. You know the algorithm of decision tree.
I don't know.
Okay. Then this decision tree gave us a hint.
This is only algorithm. This is all algorithm for predicting
Yes, the result. It's not an algorithm, it's the result.
result.
Algorithm is simple. So you see the data set, and then you divide. There are some features. Features means it's 1,000 vectors. One of the coordinate is very important because it divides these two classes the most important, most efficiently. Then you use that feature. Here it's A1000, and you divide those data set into two parts using this A1000. And then after that, now you search which is the next most efficient division. And then that turned out to be this 343. And then it divides the data set according to the value, and then etc. And then from the division,
It's kind of bisection.
Okay. That's the decision tree. That's the machine learning algorithm. And then this is the result. Now we can interpret this. And then the interpretation is here. And then now we know number theory. We try to prove it. Actually, we could prove it. Well, actually, we could do more. And we didn't stop at 9 because 9 is something squared. So we did for L squared, and then it worked.
I think in numerical analysis, we have more elegant analysis or better than bisection.
Of course, this is a very elementary.
The Newton method.
Elegant means probably it's also complicated and beautiful. But here, this is a very simple method, works, and then works so well. And this is one example. Of course, in the next example, I will show you transformers. That's much less simple. But then, of course, we can apply very high technology in numerical analysis and in many other fields.
I see. Now I understand.
Okay, good.
You plug in all the coefficients from A1 to A1000, right?
Yes.
But if you plugged in all the coefficients between 1 and 999, because the first one,
we didn't do that, but it seems that probably the model could recognize
the cubes.
Of course, this choice of 1,000 was kind of arbitrary.
It was arbitrary, but it was important because it's cube.
Yes and no. In the end, the important things were prime cubes.
Okay.
It was like a combination of 2 cubed and 5 cubed.
Well, why 125 doesn't appear in this?
That's a good question. And then the statement is for some prime, not all prime.
Yes. Okay.
Okay. So, and then, yeah. Now, this theorem has been accepted, not yet published. So, again, my point is, this gave us a new perspective. Then, luckily enough, we could get a theorem. And we did a similar, but different experiments for degree 8 case. And then there is abelian and non-abelian. And then there are many degree 8 Galois extensions. And decision tree is much more complicated. So if it becomes really, really complicated, and then if we cannot recognize the patterns, then basically it may not work. So the first example was very simple and basic, and then was a nice example. But this is a much more complicated. But if you look at the branching points, then we have 23 squared, 17 squared. So everything is like a square. So we again analyzed the situation and then made a conjecture, and we could prove some new criteria for determining the Galois groups for degree 8. So we did like a binary classification, so only abelian and non-abelian. They could prove this. And then again, we found out that this is a new result. So yeah, our our skip the detailed explanation. The point is, this works. Now we come back here, then we can compute the predicted zeta coefficients, and then we can immediately determine the case of non-abelian extension. Actually, it is a D4. But there are two non-abelian groups, so D4 and Q8. And then, of course, we wanted to distinguish D4 from Q8, but decision tree became very complicated. So even though we obtained this high accuracy, about 98 accuracy, but decision tree was complicated. Then in this case, we could not come up with a nice conjecture. Even though machine is performing very well, but for humans, still the interpretation is a challenge.
So in what sense your accuracy?
Huh?
Your accuracy 98.8%. What do you mean by that?
As usual, so you have a data set of, in this case, 100,000. You choose 70% for training, and the other 30% is separated for test. And now 70% of them has labels. One is abelian and the other is, in this case, D4 or Q8, D4, binary classification. And then presented those test data points. And then the machine will tell you which one is D4 and which one is Q8. And the accuracy is about 98%.
It's kind of, I think, if you have data set, you divide the two parts by sex, right? And
no, it's not. This is a decision tree still, but it's labeled data set. It's like a dogs and cats, and then you have pictures of dogs and then pictures of a cat, and then give a picture to a machine, and then the machine will tell you if this is a dog or a cat. It's the same thing. And then here we may use like a neural network or convolutional neural network, where there are many possible algorithms. But here we are using decision tree.
So it's maybe just the question is maybe the mesh size is one half, right? Each part you keep you go another step, next step, then one half.
Not really. So sometimes like a majority maybe 90%. It's like in the one half. What do you mean by one half? It's like a finite element method.
No. This bisection method is just kind of mesh size 8, 1/2, 0.5, right?
They can be determined by the data set. It doesn't need to be like exactly in the middle. Actually not. So whatever the point may be the most efficient, it finds out that point. It may be like 90% of the data set, but if the division may occur here, if that's most efficient, it doesn't need to be half. This is like a Q8, it's a D4. And after that, we use different features and you define it further.
Yeah, I think yes. We have some error analysis. It's kind of a error analysis. It's similar to.
Yeah, there should be similarities. Okay. So yeah, the point was, even though we see high accuracy, sometimes interpretation is not straightforward. Then you need to do something, do more to extract the information. Okay, that was the first example. I think we are good with time. So Professor Youngju Choi is here. Okay. I visited the postdoc many years ago at that time.
She's there.
And she invited me. Okay, now let's move on to the second problem. And then it's about Catalan numbers. Have you ever seen these numbers, Catalan numbers? These numbers are the second most frequent appearing numbers in mathematics, or in at least algebraic combinatorics. The first one is, of course, binomial coefficients. These are second most frequently appearing numbers. And Richard Stanley, who is the godfather of algebraic combinatorics, wrote a book on Catalan numbers. And then in the book, there are more than 200 algebraic combinatorial characterization of Catalan numbers, more than 200. Okay, and then those 200 characterizations are all exercise problems. So, and then one of the most basic combinatorial interpretation is Cn equals the number of dyke paths with semi-length n. So what is a dyke path? Dyke path also appears in many places. Indeed, many places like algebraic geometry. And whenever you do some kind of combinatorics, dyke paths begin to appear, or in mathematical physics, and like number theory too. In any case, a dyke path is like this. It's you consider n by n grid, and then you start from 0,0 and ends the path starts at 0,0 and ends at n, and then the path can go up or to the right, but it cannot go below the diagonal. It may touch the diagonal, that's fine, but it cannot go below the diagonal. The figure is created by Kyu-Hwan. But dyke path can be considered as a word or a sentence. If the vocabulary is only 1 and 0. Like up arrow is 1 and right arrow is 0. And for example, this dyke path can be considered as a sentence. And each dyke path has 3 associated statistics. So yeah, in order to explain the problem, so let us think about these statistics. So first, the area. Area is easy. Here is a diagonal like a line in the dyke path. And you count the number of whole boxes, whole cells. Like half boxes are thrown away. Just count the number of whole boxes. And then we have these numbers 0 because there is no box. 1, 2, etc. Then let's call this sequence from bottom to top the area sequence. then obviously this is a very basic statistics. Combinatorial, and the area is 13. Bounce means you launch a ball from here, and then just follow the bounce path. It's a ball, and then it hits here, then it changes the direction, and then it hits a diagonal, then it changes the direction, etc. Then we have these points on the diagonal, and then you calculate the bounce statistics using that formula. So it's an easy thing. In this case, it's 7. Then DINV is a little bit involved, but it's kind of computing the number of inversions. So if you study like permutation groups, and you count the number of inversions, similar, but it's using area sequences. That's the definition. Then the point is, it's easy to compute. Then you can compute the DINV, diagonal inversion. Okay, and then the main interest is in Qt Catalan numbers. There is a official definition, or more like a rigorous, more algebraic and some original definition. But I will not define Qt Catalan numbers in that way because it takes time. So it's a Qt deformation of Catalan numbers. So if you plug in 1 and 1, and for Q and T, then you get Cn. Okay. And you may consider this as a definition of the Qt Catalan number. So here pi is over type path. Then because it is the deformation of the Catalan numbers, so that's natural. And Q to D area of pi, and T to D of bounds of pi. Okay, and that's the definition of Qt Catalan numbers. So interestingly, I think it's due to Hyman. Interestingly, Hagelund, about the same time or slightly later, found out that this is equal to this. So Q to the dim of pi and T to the area of pi. And then we have this equality. Oh, that's good. So we have not one definition, but 2 equivalent definitions. But at this point, combinatorialists would like to see a bijection. A bijection from this set to the same set, okay, and which swaps the area bounds and to like a dim area. This formula suggests that there may be such a bijection, like a nice bijection. It's some combinatorial bijection, because these 2 formulas are equivalent. And that's what Hagelund did. Hagelund showed that there is a bijection. He called the map zeta map. And on the set of type paths that exchanges these statistics. And then this algorithm is, of course, known. And then the bijection can be given as an algorithm. But it's a non-trivial. It's not a trivial fact, trivial like a manipulation. It's non-trivial. And then, but it's interesting. And then Qt Catalan numbers still have some open problems. So in any case, so my point is, okay, so we have this bijection in here. And question, this is a non-trivial and interesting bijection. So can machine learn the zeta map? Of course, we will not tell the machine what the algorithm is. And then can machine learn the zeta map? Okay, that was the question we asked some time ago. And if successful, then can it recover one of the known algorithms or something else? So machine may think differently. Okay? We human beings have some like a way of thinking, but machine may see something different, and then what will happen? So there was the question. So the experiment was this. This was the input, and the image of the data map is the output. Okay, so the input and output. We can consider this as a sentence. Okay, in English. Then if this is a sentence in French. Okay, and then this is if you look at this problem that way, this is a translation. And translation can be efficiently performed by a large language model. Not large language model, but a transformer. Because transformers were designed for translation. So this is a translation task. And then we thought that transformer can be used in this task. So we trained transformers, so in particular, some small transformer designed by Francois Charton.
So in what sense do you say zeta map is bisection?
Bijection, yeah. Yeah.
Wow. Why?
Oh, what do you mean by why?
Zeta map, what do you mean by that? Maybe
what I'm saying is that there is a bijection, and then we call the bijection the zeta map. That's just name. It's like what kind of bijection we have? A famous bijection, maybe. Anyway, so that's the name. So you probably missed that, but it is a name. There's no why. I was surprised because you asked why, but there is no reason because it's a name. It's the name of the bijection. Okay, probably I should have spent.
So you introduce the zeta function, right?
Oh, okay. So accidentally the same name, but the previous one was Dedekind zeta function. Dedekind, so probably around 1900, Dedekind studied the Dedekind zeta functions. The Riemann studied the Riemann zeta function. But here, this zeta function is zeta map. It's much simpler, and then it's only a bijection. Okay. I have some algebraic combinatorics were complain the zeta map. If you consider like a C, say 20, the number of the dipaths is astronomically big, and then we have this bijection. So still, it's not.
Maybe another sense is zeta function is actually solution of a homogeneous solution of Laplace problem. So Laplace operator in some sense is mapping one set one to one. Invertible.
I'm not sure if you are talking about mass forms, for example. Mass forms are the solutions to the partial differential equations given by Laplace Beltrami operator. But here, that mass, and then we have to have probably. So in modular form case, we can apply Berlin transform. Then we get L function. Mass forms, I'm not sure. So Professor Cho, if we apply Berlin transform to mass forms, then do we get L function? Probably not. Yeah, no, yeah. For modular forms, yeah.
No relation.
Huh?
No relation.
No relation.
Okay.
There are two professors. I'm sorry. Sungman Cho. Okay. I mean, I don't know if the spellings, but yeah. So, yeah. So where are we? So we considered n equal to 11 to n equal to 15. And then again, the transformer achieved more than 95% accuracy. So all was surprising because it learned the bijection. But of course, the next question is how or why how this transformer is seeing the bijection. So we interpret this model for n equal to 13. And then this is the architecture of a transformer. If you're interested in machine learning and AI, then probably you saw this. So there is an input and then some neural network. And then this is a encoder. This is a decoder. So this part produces the output. But here, important thing is there is a cross attention given by this. When it produces the output, it sees it. I mean, the decoder sees the information coming from the input, and then all these things are basically written in matrices, so we can print out the matrices. Okay, and we only considered very simple model, so we really could see the cross attention matrices. So we can track the cross attention matrices step by step throughout the output generation. So this was the result. So these are our cross attention matrices. So let me magnify one of them, the first of them. And here, the blue path is the input, and then this dashed or dotted path is the output, and this is the cross attention. And if it is a dark or almost like black, that means transformer is ignoring those steps. So this is the length 13. So there are 26 steps. Let's see. So from 0 to 25, 26 steps. And then transformer after training is ignoring all the other steps except these 4 or 5. Okay, except these 4 or 5, less than 4. But this is quite dark. It is ignoring all the other steps. And then what are these steps? Yeah, those are corresponding to that red segments. Somehow, when it produces the output, it ignores, and then it produces the first step. It ignores all the other things, then only pays attention to those 4 steps. And then can you characterize those 4 steps? Those are corners. Then moreover, only horizontal corners, not vertical ones. Somehow, after training, transformer is ignoring all the vertical steps. And then it only looks at horizontal steps, the corners, and then farthest away from the diagonal. So there are other corners, like this is another corner, but that corner is ignored, completely ignored. It only pays attention to the farthest away corners from the diagonal. Oh, that's interesting. Okay, in this way, we can interpret how transformer sees the picture, so step by step. So at first,
encoding, decoding at the same position, at the four corner. They have some kind of invertible encoding or decodings. So your bijection is kind of invertible mapping is inverse, right? No, can I imagine like that?
So it's like you have a sentence. Say, I'm a boy. Okay, I'm a boy. Then after encoding, it becomes the vectors in high dimensional space. In this case, 276 dimensional. Okay, that's encoding, and then that's like input. We can consider that an input vector. Now the translation, that's a decoder. So when it sees I, then if it is like Korean, 나는 소년입니다. Okay, so then I should be somehow it produces na는. Okay, then that's decoder part. And then, but it sees not just I, but it sees the context. So that's like a cross attention. This is like I'm a boy, then it now what produces the word na, but it sees not only just I, but it also sees the other parts, so that it may translate in context. That's what a transformer does. So it's not like a invertible map, but it's more complicated. It's a nice matching. So after that, the second is that's the first step. The next step is after producing na is or na는, and then it sees I'm a boy again. Then it also remembers 나는, and then it knows after training, it knows 소년 should come next, etc. And then this is the process. But here everything is 1 and 0. Okay, so after analyzing some examples and following the thinking of the transformer, we could come up with an algorithm. So this is we call this algorithm scaffolding algorithm. And then as far as we know, this is a new algorithm, but it's coming from the transformer. We interpret the thinking of the transformer, and then we could come up with a new algorithm, which is called the scaffolding algorithm. So this was very interesting for us. So I will explain the algorithm. There will be but I will not give you a pseudocode. There will be very boring. So think it this way: there is a shuttle. You play StarCraft. Then there is a Protoss shuttle. So the shuttle has 2 agents. One is worker, and the other is a ninja. It lands somewhere, and then ninja and worker will come out. And then ninja only moves vertically. Ninja, can scale walls so vertically. And the worker can only move horizontally. Okay, and then during the process, they will report their positions. Okay, and then according to the information, the output will be built. Okay, that's the basic idea. Yeah. Coco-Hwan, Xiaoyu is nickname Coco. Coco created this website. Okay, so first step, or shuttle arrived there because it's the file. Somehow in the end we came up with this. Anyway, so shuttle arrives here, and then another shuttle. Okay, and then they report their positions. Meanwhile, these 2 segments have been built. Now, what's the next step? Worker came out, another worker, a ninja, vertically. Okay, and then because it's the same stage, meanwhile, other shuttles arrived. Okay, and then now they report their positions. As they report their positions, the output of die path is being built in the seed. Then next, what's happening? The worker has moved horizontally. This is old worker. The new worker came out. There's no more ninja because there is no vertical space anymore. If it is a big example, then there will be several ninjas. The ninja will move. And then in this way, we got an output, and this is we have proven that this is really equivalent the known algorithm, but it is different. So in the known algorithm, it uses the area sequence. Here we don't really use area sequence. Of course, in order to show the equivalence, in the end, we have to convert these process using area sequence, and then several translations, and then we match. But here, as it is, we don't use area sequence, but we get the same thing.
So area sequence means the area is large, then you change direction.
Oh,
Yeah, something like that, right?
yeah, something like that. It's more, yeah. Anyway, so something like that. So there is a very concrete algorithm. Okay, I'm exactly on time. Then, thank you for your attention.
Thank you very much for the talk. And any question or comment? That's yeah.
여기 카메라가 있는. 최영주 교수님 안녕하세요.
네, 교수님. 네, 너무
야.
잘 들었습니다. Thank you
혹시-
for your beautiful talk. Can you hear me? 들리세요?
나
야.
들리세요?
죄송합니다. 지금 소리가 안 들려서
하이. 예, 안녕하세요.
오랜만에 뵙네.
Yeah. Okay. And any question or comment, audience? Let me ask. Yeah, please. No, please.
So there's many other like quantities in algebraic combinatorics that can be indexed by, let's say, sequences of ones and zeros or things like that.
Let's pass.
Yeah, have you tried something else? Do you think this is very general? Like,
I am trying other things, of course, but the most challenging thing is that when it's like a real project. So if you see the definition, algebraic definition of the Qt catalog numbers, then this is true. And this is easy to see. It is natural if you see the algebraic definition. But combinatorially, then the people expected that we should be able to switch area and bounds, and then bounds and area. So if you remember, then it was a div and area. So there was a third statistics. But because of this, they wanted to find out the combinatorial bijection, which is swaps area and bounds. And not the third one, just the area and bounds, because this is true. But combinatorially, it is still open problem. And then nobody could come up with a bijection. And then this is an interesting problem, but obviously difficult problem because it has been open more than 20 years. And if we can construct a bijection, which swaps these two statistics, then there will be a fantastic. I mean, using AI. So we tried a few things, but so far it's difficult. But still, we hope that we can do something. And then there are many possible examples, because of course we have many different kinds of lattice paths.
Can I ask a question? So, may I ask you what kind of math problem is approachable by AI? Is it?
Oh, yeah, that's a good question. Really good question. Then we have tools. Like a large language model themselves are tools. And then we have also like transformers. Have you ever heard of alpha evolve? Oh, okay, alpha evolve. That's another tool. Alpha evolve. Anyway, so there are many tools. Some tools are really useful for certain types of problems. For example, alpha evolve is really good at optimization problem. So if you want to have examples like breaking the known upper bound or lower bound, alpha evolver have been very successful. So if you have not seen it before, is this just
I think
internet
yeah,
program?
I think we can connect.
Can I just this?
I believe, but
If something changes, so
yeah.
alpha evolve, yeah. Yeah, so then they apply this to mathematics problems. Then
So you use this machine learning, this algorithm.
yes.
So this algorithm is
I mean, this is a system, not an algorithm.
maybe this kind of software you say.
Yeah, Terence Tao was this one, yeah. So you have not seen this paper? And yeah, this is a really interesting paper. Yeah, Terry Cowell is one of the authors. And if you go there, and they studied about 67 mathematics problems. Yeah, 67. And then they broke some known like records.
So do they talk about the convergence of the edge data set increase?
No, it's not like this. So it's a different like approach. So for example, like kissing numbers or sphere packing. Packing problems.
Mm.
And then like 67 problems. And then in some cases, they broke the examples. Like if there is a known bound, then they broke the examples and the bounds. The idea is this. You have a Python code, and then you ask the large language model to make the code evolve. So then the model will search for the space of code, Python code. Then it modifies the code a little bit. And then there is another evaluator, and the evaluator will evaluate the code and then see the score. Then if there is like an improvement, then it gives you some reward. It's like a reinforcement learning. And then if it gives a worse score, then it just throw it away. And then it considers like thousands and millions of code. And then you run it like overnight. Then it evolves little by little. And in the end, it breaks the record. I mean, that happened for here are 67 problems, like about 12 problems. They found out new records. For example, like hacking problems like this. Yeah, of course, you have to read the exact details, but yeah, like this. So there were previously known bounds, like anyway, so these things. And then everything is given through Python code. So you can really evaluate, but you don't do it. Alpha evolver will do it for you. And then you just run it for a long enough time, then it evolves little by little. And then it finds out better and better approaches. And then later it breaks the record. It's very, I mean, you have not seen it before, then yeah, please look at it. This is another tool. Then this is good for upper bound and lower bound. It's not like a Galois problem. So in order to answer your question, it is experimental science. So you can try to formulate some categories, and probably people are trying to do that. But so far, there's no like, one answer. So you know which tools are available. Then you know the pros and cons, then strength and weakness. Then you also have to understand the math problems. Then you have to apply those things. So it's like more like heuristics and practitioners. But another point is, if you have a huge data set, then that's a really good start. But in this case, you don't need a data set. A data set is a really good start for this kind of optimization. And there may be some other categories. Nobody has really characterized those problems exactly. But people are accumulating their experiences.
Actually, from your picture, from origin to the one diagonal point 1, 1, actually, it's kind of two. You need to find the vector field, right? You need this kind of vector. So the vector is like a trajectory mapping.
In the typeface case.
Yeah, trajectory mapping. So the vector field can be governed by some PDE, partial differentiation, right?
Yeah.
Some kind of simple Laplace problem or Stokes problem, something like that.
That's actually really good idea. And then I think maybe these days the internet is available, so there is a paper using that kind of idea. It's not exactly that idea, flow boost. Archive. And then I mean I cannot go over the details but my point is you may find out something like that in this paper. It's flow boost. So we're using flow boost. So the idea is distribution. Okay, distribution. You transform the distribution from one probability distribution to the other. The process will be given by some gradient flow. So not exactly this paper. So I'm trying to find a flow with paper. It didn't show up. Anyway, there are some papers and research related to that. Anyway, so probably you can find them.
Thank you. A pure mathematical problem can be solved by applying mathematician tool, right?
I see. We have more tools.
And one last question is maybe, do you have any suggestion or advice to students how to use this AI tool or how to live with AI?
Open your mind. There are opportunities, and then don't be afraid of adapting new things. I believe probably you already feel that things are changing, and the mathematics research probably will change, and then you see the impact sometime soon. I believe, So then it's better to be prepared. So open mind, and then don't be afraid of using something new. And of course, we keep the tradition and the traditional things. That's important. At the same time, we have to be willing to accept new things. you can use large language models because it's getting smarter and smarter. So the GPT or Claude can be your best friend. And then studying, another thing is just using those things without understanding is dangerous. So if you have time and energy, and I strongly suggest that you study the theory behind it. Oh, that would be very helpful. So many people just use AI as a black box. But if you understand those inner mechanism, then that's a huge help. So of course it takes time and energy, but whenever you have time, if you have time and then some interest, then I strongly suggest that you study some basic things in AI systems.
So as data set, your data set is large, so you cannot believe, right? Your result, right? You don't believe. How can you believe? Because you don't have a stability for your algorithm.
So that's why we try to prove it.
You say you just you something you go, then you something you throw away, right? Then you have some error. So maybe finite step is okay. Maybe going further,
Yeah.
Maybe you don't believe, you cannot believe.
I mean, so probably you're talking about this the mother person. But anyway, so yeah, if
worry about that.
if error is accumulated, then in the end, we cannot believe it. Yeah. So that's the danger of this AI. Yeah.
Yes, we have roundup error, right? We have finite decision precision, right? Then roundup is large, data is large, the error is blow up. So your result is not trustable.
So that's why we have to be rigorous at some point, step by step. Otherwise, in the end, we will get hallucination. So always we have to check. That's right. I totally agree with you.
Okay, so thank you very much. So let's thanks to Professor. So this is last colloquium talk of this semester. So thank you for participating and have a nice vacation.